Discovering Geometry with Mrs. Berry. This is Lesson 70. Today we're going to talk about trigonometry and problem solving with right triangles. Right triangle trigonometry is often used indirectly to find the height of a tall object or maybe some distances when you have a triangle. So when we're using the height, when we use right triangles, we often talk about the angles of elevation and the angles of depression. And really that is just from the horizon, if you're looking down, that's the angle of depression. Or from the horizon, if you're looking up, that's the angle of elevation. To solve a problem of missing height, measure the angle from the horizontal to your line of sight when you look at the top or the bottom of an object. If you're looking up, you're measuring the angle of elevation. If you're looking down, then you're measuring the angle of depression. So the angle of depression is more when you're going to be on top of a tall tower, in an airplane, in a hot air balloon. The angle of elevation is usually going to be used when you're on the ground, looking up at a taller object. Our first example. The angle of elevation from a sailboat to the top of a 120-foot lighthouse on the shore measures 16 degrees. To the nearest foot, how far is the sailboat from shore? So the first thing we want to do is draw a picture of what this might look like. So let's say we have our lighthouse. We have our sailboat. So we have the height of the lighthouse is 121 feet. So the horizontal from the sailboat to the bottom of the lighthouse, we're going to assume is just flat. And so looking up to the top of the lighthouse is where we're going to have our angle of elevation. This is 16 degrees. Now to the nearest foot, how far is the sailboat from the shore? So this is our x. This is what we're looking for. Next, we want to think about what trig ratio we're going to use. So if we have this as our angle, and we know the height, but we want to know the distance in the horizontal, what trig ratio are we going to use where this is our angle and we have this side and we want this side? So this is the opposite that we have and we want to know the adjacent. That means we're going to be using tangent. Here's our picture again. We want to know the tangent of 16 degrees, and it will be equal to the opposite over the adjacent. So it'll be equal to 121 over x. Now the tangent of 16 is 0.2867, and that is still equal to 121 feet over x. Right now we don't have a good way of getting x. If we use algebra, we can multiply both sides by x. And that means that on this side it cancels. So we have 121 is equal to 0.2867x. Then we'll divide by the 0.2867. So our answer is going to be x is equal to 121 divided by that tangent of 16, if you want to type it all in at one time. But that tangent of 16 is 0.2867. And that means that x is going to be equal to 421.977. And we want to round to the nearest foot, so we're going to take it as 422 feet. Now we have one more example. A ship's officer sees a lighthouse at a 42-degree angle on the horizon to the right of the ship's path. After the ship travels 1,800 meters, the lighthouse is at a 90-degree angle to the ship's path. What is the distance between the ship and the lighthouse at this second sighting? So this one might be a little confusing because we're not seeing an angle of elevation or angle of depression. Where is the angle? Imagine this one as a bird's eye view. Here's our lighthouse, and here is our ship. And our ship is traveling this direction. So this is the ship's path. And now we have the first sighting when the ship is down here is at a 42-degree angle. So this right here, 42-degree angle from the ship's, or to the right of the ship's path. So if the ship is going straight up, then to the right would be 42 degrees over is where we see the lighthouse. Now the ship travels 1,800 meters. And then it is directly making a 90-degree angle here to the lighthouse. So this is what our picture should look like. What is the distance between the ship and the lighthouse at the second sighting? So this is the first time, and this is the second time. We want to know this distance between the second sighting and the lighthouse. Here's this picture again. I just moved it over so that we could do our work. What trig ratio are we needing? We have an angle, we have this side, and we want to know this top side. So even though this triangle is in a different direction, this is our 90-degree angle. So this one is our hypotenuse, which we don't need. We are still working with adjacent and opposite. So we're still working with tangent. And what angle are we using? 42 degrees. So tangent of 42 degrees is equal to the opposite over adjacent. In this picture, our opposite is the x, our variable, what we want to know. And our adjacent is the 1,800 meters. When you're set up this way, where you have the trig function is equal to the variable on top times the 1,800 meters, it's a little bit easier to put it into your calculator or to do the algebra. Before I even take the tangent of 42 degrees, I'm going to multiply by the 1,800 that's at the bottom of this fraction. So now my equation looks like this. 1,800 times tangent of 42 is equal to x, what I want to know. This is easier to plug into our calculator, and we find your sines and tangents are going to be less than 1. So when you get your answer, you should be looking for something in a decimal range when you get your trig. If your answer of x, your distance, comes out to a decimal, you need to be asking yourself, are we really traveling a decimal amount of meters? So make sure that your answer makes sense. When I multiply 1,800 times tangent of 42, I get 1620.727. So I'm going to round that to 1621 meters. Now, does that number make sense? When I come back over and look at my picture, this side was 1,800. So this side should be a fairly large number. 1621 does make sense. If I had gotten a decimal number there, it would not have made sense in my picture. Make sure that you're using common sense to double check and make sure that your answer is in the right ballpark when you're doing these problems.